Okay, this is an example problem for Physics 1000, Auburn University, summer 2013. We're going to work a couple problems using this diagram to show you what all we can do with Ohm's law that we've talked about. So the first problem I'm going to work here is probably the simplest. I'm going to ask a basic question. If you were the battery, seems kind of strange, right? But if you found yourself as the voltage source in some circuit, and you gave yourself the challenge of replacing these resistors in this circuit with something that wasn't going to affect you. In other words, what you saw the circuit doing to you wouldn't change. It would look something along these lines. Your challenge is to figure out what is the value of this resistor here that's going to look to you, being the battery, exactly the same as this configuration here. How would you replace these two resistors with one resistor that's not going to affect you at all? So, let's see if we can find our way through that problem. That might be a strange way to think about it, but at least we can find our way through the math. So, this is a parallel circuit. You should be able to recognize that from the fact that the current, as it's moving up here, is going to actually split. Remember, in a series circuit, there's only one path for the current to follow, so it has to sort of barrel through all the components. In series, that's why they call it series. Here, the current is going to split itself into two parts. One's going to follow this path, the other one's going to follow this path. And we'll talk about exactly how the current splits in a later problem. The only reason I'm pointing that here is you should be able to use that to recognize that this is a parallel circuit. So the rules for parallel circuits are different than series circuits. So the formula for equivalent resistance in a parallel circuit is this. 1 over the equivalent resistance is equal to the sum of 1 over the component resistances. 1 over R1 plus 1 over R2 in this case. If I had more, clearly there'd be more terms there. I've just got two of them here. So I've got this nice little inverse equation. So there are a couple steps you have to remember here. And the first one is that this is not your equivalent resistance. It's 1 over your equivalent resistance. So after you do this summation, you're going to have to flip this guy over to get your actual equivalent resistance. So it's a little bit more complicated than the series circuit in that way, but it still shouldn't be too bad. So let's see if we can unpack this. I'm going to go to the next page because I'm running out of room here. So, if you remember, my R1 was 10 ohms, my R2 was 15 ohms, and my formula here, 1 over R equivalent, which I'll just call R for the sake of me not writing with the stylus, equals 1 over R1 plus 1 over R2. And if I just plug in numbers there, I'm going to get, that's 1 over 10 ohms plus 1 over 15 ohms. So at this point we can apply all the rules of fractions that we know. So we've got to find least common denominator there, which I believe in this case is going to be 30. So I'm just going to rewrite this in with new numbers. If it's been a while since you did this, that's okay. Basically, I've rewritten these fractions in a more complicated form, but if you notice, if you reduce this fraction, it ends up being this fraction. If you reduce this fraction, it ends up being this fraction. The only thing I've done is put them in a form where I can easily add them. So that's going to equal 5 over 30 ohms, which is just equal to 1 over 6 ohms. Now, what I've done is I've calculated 1 over my equivalent resistance. And that's not a G, should be a Q. So if I want to find the actual equivalent resistance, I'm going to have to flip this fraction over. Notice if I flip both sides of this equation, and the mathematical term would be I take the inverse of both of these terms, I get our equivalent is equal to 6 ohms. And that's nice and pretty. In general, you shouldn't expect it to be a nice number like this. You're probably going to get a fraction on the right side of this equation. That's totally okay. But in this case, I get a nice 6 ohms. So let's talk about what this means. I'm going to go back to my first page, and I'm going to erase some of the stuff that's going to get in my way. What that means is that if I built both of these circuits where this resistor here is 6 ohms, which is what I've found the equivalent resistance to be, from the perspective of the battery, there's no difference between these two. Exactly no difference. The current at this point right here, just like it is at this point right here, is going to be the exact same in both situations. Now, in our original one, the current gets more complicated because we've already talked about how it's going to split. But from the perspective of the battery or the voltage source, the current that's flowing in and out is exactly the same. So, what that says is that this is reducible to this. And again, you might ask yourselves, why do we need to do that? Why do we care? Well, as it turns out, some problems are a lot easier to solve if you look at the equivalent resistances as opposed to the original resistances. It just depends on what you're being asked to solve. So that's how you handle equivalent resistances in a parallel circuit. There's a video on how you solve equivalent resistances in a series circuit. We'll get to some more complicated problems on the next videos. Thank you very much. I'll see you next time.